Okay, welcome. Today we are going to work through the solutions to the first quiz. So the quiz scenario for the first 6 questions, we have Eva, Mateo, and Aiden are 3 friends who participate in a monthly math competition. Each month the probability that Eva will score higher than Mateo is 50%. The probability that Eva will score higher than Aiden is 90%. And the probability that Eva will score higher than neither Mateo nor Aiden is 5%. Okay, so I'm going to start by just writing down what we know. So let's see. First of all, I'm going to call A the event that Eva scores higher than Aiden. I'm going to let M equal the event that Eva scores higher than Mateo. Now I'm told that the probability that Eva will score higher than Mateo, so P of M, is 50%. So writing that as a probability, 0.50. And the probability that Eva scores higher than Aiden is 90%, so P of A is 0.90. And I'm also told the probability that Eva will score higher than neither Mateo nor Aiden. So this would mean Eva is higher than Aiden, no, and she's not higher than Mateo either. Right? So this is the event that I'm looking at here. Probability that she scores higher than neither is 5%, so 0.05. So part of this quiz is getting used to thinking about how to take something written in words and think about what we're looking at in terms of set notation. Okay, so now I'm just going to start working with this before I even look at the questions. So often if I have a situation with 2 events like this and I want to think about it, it's often helpful to start with a Venn diagram. So I'm going to use a Venn diagram. Here's my outcome space. And I'm thinking about the outcome space in terms of this. I know the probability, I've got sort of event A, Eva scores higher than Aiden. Probability is bigger than of her, so I've got, say, Mateo, beating Mateo. And then I've got the part outside of that. So not beating Aiden and not beating Mateo, that's this outside part here, and that is 0.05. Right. Now, since the total probability of this entire outcome space has to add up to 1, I know that the probability of this part has to be 0.95. And this is either beating Aiden or beating Mateo, or both. So that's the union. So the probability of A union M, beating Aiden or Mateo. This is the complement, remember, of beating neither Aiden nor Mateo. Is 0.95. So I've got 0.95 in this whole piece. If I want to think about sort of how that's all distributed, I'm going to start by trying to figure out, whenever I'm drawing a Venn diagram, I always think it's easiest if I can figure out the intersections first. Right? So I'm going to say, okay, well, I know that the probability of A union M, beating Aiden or Mateo, is equal to the probability that Eva beats Aiden plus the probability that Eva beats Mateo, minus the probability that she beats both Aiden and Mateo. Now I know the probability of the union is 0.95. I know the probability that she beats Aiden is 0.90. I know the probability that she beats Mateo is 0.50. So I can solve this to find the probability of that intersection. And when I do, I find that the probability of the intersection is equal to 0.45. So I've got I wrote that incorrectly, 0.45 in the intersection here. The total in the Mateo part is going to be the probability of beating Mateo and Aiden plus the probability of beating Mateo but not Aiden. Right? And this part here represents beating Mateo but not Aiden. I know this is 0.50. The probability of the intersection is 0.45. Which means that the probability of beating Mateo but not beating Aiden must be 0.05. So there's our probability there. Right, and this is because, remember, if I'm thinking about the probability, I'm breaking this up into mutually exclusive and exhaustive intersections of events here, probably of Mateo and Aiden, plus the probability of Mateo and not Aiden, all the possible ways we could beat Mateo. Then, similarly, I can find the probability of beating Aiden. We know is 0.90. It's got to be the probability of beating Aiden and not Mateo, plus the probability of beating Aiden and Mateo. Aiden and Mateo is 0.45. Whoop, sorry. I put these in the wrong order, but the probability of the intersection here is 0.45. Probability of the intersection of beating Aiden and not Mateo, I just did those in the opposite order on that line. That shows me the probability of beating Aiden but not beating Mateo is 0.45 also. So now I've kind of figured out the probability of sort of all of the possibilities in my outcome space in terms of Eva beating each of the friends. And so now I'm going to go back and look at the questions that were asked. Okay. So I want to find the probability that Eva scores higher than at least one of her friends. That would be the probability that she scores higher than Aiden or Mateo or both. That's the probability of Aiden or Mateo being higher. And I found already that the probability of that union is 0.95. The next one is asking the probability that Eva scores higher than Aiden but not Mateo. So here we're looking at she higher than Aiden and not higher than Mateo. Here we go, that's this part of the Venn diagram here. She's higher than Aiden but not higher than Mateo is 0.45. The probability that Eva scores higher than both Aiden and Mateo, higher than Aiden and higher than Mateo, again, that's this part of the Venn diagram here, 0.45. The probability that she scores higher than one of her friends but not both, higher than one but not both, so that would be if she's higher than Aiden but not Mateo, or if she's higher than Mateo but not Aiden, so those are these two pieces here. So that gives us 0.50. And those are all the ones we're looking for. Now question 5 asks true or false, Eva scoring higher than Matteo and Eva scoring higher than Aiden are mutually exclusive. For events to be mutually exclusive, we'd need them to have the probability of the intersection to be 0. But here we know that the probability of the intersection of those events is not 0, so this one is false. 6 asks true or false, Eva scoring higher than Matteo and Eva scoring higher than Aiden are exhaustive. Events are exhaustive if the probability of the union is equal to 1. At least one of them must happen. But in this case, the probability of A union M is 0.95. We can see it's possible that she beats neither. So that one also is false. So that brings us through those first set of exercises. Okay. So now I'm going to kind of switch gears to the counting questions. Looking at counting, remember when we use permutations when we're interested in the number of ordered arrangements? We use combinations when we're interested in how many different possible subsets, unordered subsets. So in question 7, we're looking at how many different ways, and I'll try to make it so we can see this, looking at how many different ways the letters in count can be arranged. Now here we've got 1, 2, 3, 4, 5 different letters. Each of them is different from the other. So I've got 5 letters. I'm looking at how they can be arranged. The order potentially would be mattering here then, so I'm going to be using permutations. So I'm going to be taking 5. I'm going to be permuting them into 5 places. This gives me 5 factorial, which is 120. Now in question 8, we're also looking for arranging letters. How many different ways can the letters in probability be arranged? Now here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. But they're not all different, right? We've got 2 B's. And let's see, what else? There's something else. We have 2 I's. Right? So if we were to look at just sort of how many ways we could arrange the 11 letters, we'd say, okay, well, we're going to have 11 factorial ways we can arrange those letters. But because we have 2 B's, if I count this, I'm sort of treating it like the 2 B's are differently. The 2 B's are could be arranged for each sort of arrangement of this 11 factorial. There are 2 different ways that the B's could be arranged. Right, so I'm going to divide by the number of ways I can arrange 2 B's. And there are also 2 different ways the I's can be arranged. So I'm going to divide by the number of ways the 2 I's could be arranged. And so if we're thinking about the number of different arrangements where they would look different and make different sort of words, even though they mostly wouldn't be real words, we would have 9,979,200 different possibilities. It's a lot of arrangements. Let's see. Question 9. Question 9, we have a pizza restaurant that offers 15 different toppings, but only allows customers to select up to 4 different toppings. So we want to know how many different ways there are for customers to choose up to 4 toppings for their pizza. So here we've got 15 toppings. The number of ways they could choose 0 toppings would be 15 choose 0. We don't really care the order, especially if we don't have any toppings, right? But even if we do, with 1 topping again, 15 choose 1, how many ways we could have 1 topping. But even once I have 2 toppings, I really don't care if you put on the peppers first or the mushrooms first. You're going to spread them all over the pizza. It's a mushroom and pepper pizza or whatever I said anyway, right? So I don't care about the order. I'm just going to choose 2 toppings. Here's the number of ways I could choose 3 toppings, plus the number of ways I could choose 4 from the 15 toppings. I'm just going to add those all up, and if we go through this, we should come up with 1,941 different possible combinations of pizza. Now, just going to do a little aside here, because I see I've done these things in the calculator. I want to kind of make sure people know how to use their calculator to do this. And I'm only going to demonstrate on a TI-84, but if you have another graphing calculator, if you go into YouTube and look up how to use permutations and combinations on your calculator, I'm sure you'll find a video. That's how I first learned how to do this with a TI calculator. So if I want to calculate, say, 5 factorial, I can do 5, and then I go to the math. Just make sure we see here, math. And then scroll across till we get to the probability part. And then scroll down to the factorial. Press enter again, and it does the calculation for me. If I wanted to do, say, 5, count the number of possible permutations of 5 objects into 5 spaces, I could also do this by taking 5, going to math, going down to the permutations, number of ways I can permute, and 5 into 5 spaces. Again, gives me 120. So same calculation. The permutation would be useful if I had, say, more objects than spaces I wanted to fill. I would need that one. For calculating the number of ways we could have, say, subsets of size 3 from 15 objects, I'd do 15, go to the math button, across to probability, scroll down to NCR, and then I'm choosing 3 toppings from the 15. Gives me that value here. This part of it would be 455. So just to make sure you're kind of working with your calculator. You shouldn't be having to, sort of do lots and lots of multiplication on your own. You should be able to use your calculator in most cases to do this for you very quickly. Okay. And then the last question is another counting question, and I think this is the most challenging question on the quiz because you really have to think about it. So we've got a youth soccer team that consists of 12 players. When they have games, they play simultaneously on 2 fields, so the team is divided into 2 groups of 6. We want to know how many ways can the 12 players be divided into 2 groups of 6 players if we only care which players are grouped together. Now, we don't care about order, we only care about sort of who's in each subset, so we know we're working with combinations. So the first thing we do is say, okay, well, we've got 12, and we're going to choose 6. Right? And a lot of times, like, okay, probably most people stopped right there. But this is where you have to think about the subtleties with counting. Counting is tricky, much harder than you'd think. Right? So imagine for a minute that I have my 12 players, and I'm going to pretend their names are A, B, C, D, E, F, G, H, I, J, K, L. They're my 12 players. Right? Now, suppose my first one, I say, okay, the first thing I could do is I could put A, B, C, D, E, F all in one team, and I choose those. That would be one way I could choose 6. By default, I have also created a team that has these 6 together. Later on, if I'm counting the number of ways that I could choose 6, choosing these is also going to be another way that I could choose 6, but it's going to end up making the same formation of teams, right? So if I do 12 choose 6, I'm actually counting each sort of formulation, division of teams twice. So to get the correct answer, I need to divide this by 2, because I don't really care which team is which, I only care which way they're grouped. And so what this should give me is 924 divided by 2, which is, let's see, 462 would be my correct answer. So as I say, that one's a little tricky because it seems very straightforward when you first think about it, but it results in double counting if you just do the number of combinations. So hopefully these solutions helped you figure out where you went wrong if you did on the quiz. If you find you have any questions, please don't hesitate to ask. You can do it either on the help discussion board, or you can come to an office hour, or if you can't make it to my normal posted office hours or you're off campus, you can set an appointment for an online office hour or an on-campus office hour at a different time. Have a good day.